Welcome back. This is the second recording for day 4. We're going to be tackling more cographs. Before we do that, I do want to mention about the quadrantal unicircle angles because they are very important to make the polar graph by hand. Okay, so by that, what do we mean? Well, if I have my unicircle, going back to our trigonometry, remember unicircle will look like this. Okay, and my coordinates for here will be 1, 0, 0, 1, and negative 1, 0, and 0, negative 1. And I know that the x-coordinate is always the cosine of the angle, and y-coordinate is the sine of the angle. Okay, so this tells me that cosine of 0 degrees, or 0 radians is right here. Cosine is my x-coordinate, in this case is 1. What about cosine of pi over 2? Cosine of pi over 2, the angle measure is right here. What is the cosine? It's going to be the x-coordinate is 0, is 0. Cosine of pi is cosine of pi. And pi radian is right here, 180 degrees. The x-coordinate is negative 1. And then finally, cosine of 3 pi over 2 is going to be 270 degrees right here. And the x-coordinate is again 0. Hopefully, you can figure this out. If you need to draw your quadrantal unicircle, by all means do so. What about the sine? Sine of 0 radians. 0 radians is the y-coordinate is 0. Sine of pi over 2 is 1. Sine of pi, 180 degrees, so y-coordinate is 0. And then sine of 3 pi over 2 is going to be negative 1. Hopefully you remember this. Okay, so we're going to be using this, so make sure you can do this quickly and recall accurately. Alright, so now we're going to be tackling the cograph as I mentioned. So the first category of graph is what we call limaçons. This is some French word with this little accent at the bottom. It's pronounced limaçons, and the structure of the equation for this polar graph is going to be r is equal to a plus or minus b cosine of theta, or r is equal to a plus or minus b sine of theta. Okay, so you can be both cosine or sine. So that's sine and cosine is going to change the orientation, as well as the a and b, they are just some constant number. Okay, some constant number depending on the relationship between a and b, whether a and b are the same numbers, or whether a is bigger or b is bigger, or whether it's going to be a plus b or a minus b cosine theta. That's going to make the difference. Okay, so to get us started, we're going to be looking at this particular graph, and we're going to try to graph r is equal to 5 plus 5 cosine of theta. And so we're going to use the unit circle quadrantal angle that we've just talked about right there. Okay, so here angle measure is 0. So at 0 radians or 0 radians, okay, so cosine of 0 radians, cosine of 0 is 1. So that becomes 1 times 5 is 5. 5 plus 5 is 10. All right, then pi over 2. What is cosine of pi over 2? Cosine of pi over 2, that's my 90 degrees. And cosine is 0, so that becomes 0 times 5 is still 0, plus 5 is 5. And then what about pi? Cosine of pi radians, that's 180 degrees, is negative 1 times 5. Negative 1 times 5 is negative 5, plus 0 is going to be 0. And then what about 3 pi over 2? This is going to be 0. Cosine of 270 degrees is 0, so 0 times 5 is 0, so this is comes back to 5 again. Now let's see if you can graph this. When theta was 0, radius was 10, so I can mark this as 5 and 10. So we have at 0 degrees or 0 radius. At pi over 2, okay, pi over 2 angle measure is here. The radius was 5. That means if this is 5, this is going to be 5 right there. So that's going to be the point right there. And then at pi, the radius was 0. So it comes down here, and 3 pi over 2, so this is angle measure 3 pi over 2, 270 degrees is 5. Okay, so we have 1, 2, 3, 4 points. If I continued with 2 pi, it's going to get me back to 10 again. So it's going to be repeating itself. And the shape of this graph is actually, it will look like this. If I use more points, it would actually look like this. Okay, it's not the best graph, but anyway, you get the idea. Okay, and this, what does this shape remind you of? Maybe if you turned it around, you could say that it reminds you of heart. Okay, so it might be a little bit of exaggeration, but it's a heart shaped, or at least that's what mathematicians think of it as. And okay, we don't have much of imagination. But anyway, so it looks like a heart. So what do, remember the word cardiac, cardiology, cardio, that's the word that deals with heart. So we call this shape cardioid. Okay, so C-A-R-D-I, cardioid. Okay, so this is what we call cardioid shape. And what is special, what makes this shape, is that notice that this value here, 5 and 5, the A and B in this case, A and B in this case is the same. Or I can summarize this and say A is equal to B in this structure here. Okay, and we call that cardioid because it looks like a heart. Okay, all right, so that's the first shape. Okay, but I am going to talk about what happens if it was A minus B. So say if I was to graph R is equal to, let me get a different colored pen. If I was to graph R is equal to 5 plus 5 cosine of theta, this is the one that we just graphed. It will look like this. Okay, so then what if we had to graph R is equal to 5 minus 5 cosine of theta? I want you to try to graph this on the graphing calculator or Desmos. So 5 plus this time 5 sine of theta, and also, so I am asking you to graph this. So R is equal to 5 plus 5 cosine of theta, or R is equal to 5 minus 5 cosine of theta, or R is equal to 5 minus 5 sine of theta. Okay, again, because A and B, the values in front of sine and the constant is always the same. This is a cardioid shape. But I want you to pause the video and try this and see what happens, and try to graph or sketch the graphs that you find. Okay, I hope you had a chance to do that, and you would have found that the shape is the same. It's just the orientation that changes, right? So if it was they're both positive and we're dealing with cosine, then it's going to be a heart shape that is pointing to the left. Okay, but then if it's minus, then it's just flipped over the vertical axis. Sine, if we're dealing with sine, it's going to be flipped over the polar axis or the horizontal axis. So it will look like up and down like that. So cosine is left and right, sine is up and down. That's what you need to remember. But what's true is that you always have a point at the pole or the origin. Okay, so what's true about cardioid is that you must have the point at the origin. Okay, and what we've just observed here, this is going to be true for all limacons. Okay, all the limaçons, this is a big category, and cardioid is a category, one type of limaçon, and cardioid is just one type. So all the limaçon can be orientated up and down to the left or up and down like this, and that depends on the whether it's positive or negative and whether it's going to be sine or cosine. So I'm going to write that down. All of the limaçons, there's that little accent, can face 4 ways. Okay, next we're going to try to graph a limaçon with an inner loop. Okay, so remember limaçons always have this structure for the formula. You have r is equal to either a plus or minus b cosine of theta, or r is equal to a plus or minus b sine of theta. So this time let's try to graph a sine of theta. What's special about this is that these two values, remember with the cardioid, these two values were the same, okay, but this time they are not the same. But more specifically in this case, the a value is smaller than the b value. Okay, so when a is smaller than b, this is the type of graph that occurs. Okay, so a is smaller value than the b. Okay, so let's start by thinking about the values. Remember, sine of 0 degrees is 0. 0 times 8 is going to be 0, so that's going to be 5. Okay, pi over 2. Pi over 2, sine of pi over 2 is 1. 1 times 8 is 8. 8 plus 5 is 13. And sine of pi, or 180 degrees, is 0 again. 0 times 8 is 0, so that comes back to 5. And then sine of 270 degrees, or 3 pi over 2, is negative 1 times 8 is negative 8 plus 5 is negative 3. Okay, so that's what we have, and now we need to plot it. So since we are dealing with radius of 5, I am going to say call this 5, 10, and so on. So that means this is 5 right here, and this is 10, and this is 15 right here. And I can do the same in the direction. So this is going to be negative 5 here. Okay, so let's try to plot it. Okay, when angle was 0 degrees. Okay, so along this ray, the radius was 5. So it's right here. When angle was pi over 2 is right here. This vertical axis is 13. So I need to find 13, radius of 13. That will be approximately here. Okay, and then at pi, you have 5 again, positive 5. Okay, so pi is radius. Okay, so actually I shouldn't mark this as negative, should I? This should be marked as positive because we're really talking about radius. So at pi, it's going to be 5 right there. Okay, and then pi over 2. Okay, so along here, along up this direction is going to be positive, but it's negative 3. So negative 3 is going to be back there. Okay, so this is interesting. We have it goes, so if I was to connect more points, it would look like this. So it would look like okay, but before it actually goes to negative 3, what we actually have a point right there that's going to be 0. That's between pi and 3 pi over 2. So it actually goes through like this, and it's going to make a loop here, and then it's going to continue. So this is the shape you would have for limacon with the inner loop, and you can see the inner loop right there. And that's when A is smaller than B. So when this number is smaller than this number, and whether